Ladies and gentlemen, I would like to introduce Dr. Saad Jasim. I know him since many years, and he's the expert on water the reuse and water treatment. And I just want to give some detail about him. He received his PhD and the master degrees from England, from the University of Wales, Swansea, UK, and his bachelor degree from Baghdad University, since his origin from Iraq. He served as president of the International Ozone Association. He is also president of the Environmental and SG Environmental Consultant in Winston. And he served as director of Great Lake Region Office International. I think maybe he can give us some more detail because he did a lot of work on water reuse and water treatment there in Canada and United States as well. He worked. He is founding CEO for the Walktown Clean Water Center following the Outreach tragedy. I think there was a tragedy, and I hope he can also explain to us this in few words. He introduced ozone as primary disinfectant to the city of Winston in 2001, which is very important. He designed a water reuse system for greenhouse operation in Canada. He received many awards for this work. He developed project for the reuse and treatment of sewage fluent at the Qatar Environment and Energy Research Institute, where we work together. We have been in the same office. Over the past 25 years, Dr. Jasim has focused his professional engineering work on health and safety. He works on projects for removal of the cyanotoxin in surface of water using ozone and advanced oxidation process. And I guess he will talk about this again. Dr. Saad received the 2022 Ontario Professional Engineer Award. And it's the engineering medal for entrepreneurship, the engineering medal honor engineering who have contributed sustainably to advance the engineering profession. So in 2 words, he's one of the most expert in the water treatment and reuse using ozone techniques. Dr. Saad, thank you very much for being with us, and the floor is yours.
Well, thank you, Dr. Ahmed, and for the kind introduction. And it's a great pleasure and honor to be with all of you. I'm always happy to speak about how to come with solutions to deal with water scarcity, water problems, water quality, because it impacts all of us, and the bottom line, it impacts human health. So for the water reuse, some of the basics about it, it's what some people call the water reclamation. It is, we use water that's been used before for beneficial purposes, especially the agriculture, for irrigation, or in some locations, they use it even for potable water reuse. Like you go to Singapore, there's bottled water that's written on it, new water. And that's water from a treated sewage effluent. It's been reused, and it is equivalent in quality and taste to the drinking water from fresh water sources. And that, the water reuse in general provide an alternative to the existing water supplies that is being now impacted by climate change, by increase of population, and that will provide more sustainability and security for water systems. And for some reason. Okay. And there are, in general, two kinds of water reuse, if we want to explain it in that way, from a planning point of view, the planned or unplanned. The unplanned, that means the water reuse has come to a situation where the source water is basically composed of previously used water. A common example for unplanned water reuse is the occur when communities draw their water supplies from rivers, which receives treated wastewater discharge from different communities. Many cities have water discharge and water intake not far away from each other, and that's what you see the challenges. And where the planned water reuse refer to water systems that designed with the goal of beneficially reusing a recycled water supply. And the communities want to optimize the water reuse because that to provide more safety for the environment, and also use this water source for irrigation, which is the major use for water sources in most of the countries now, especially the MENA groups, which is Middle East and North Africa. So that's what gives more options of new water sources. So type of the water reuse, there are many sources of water that can be reused, and for industry processes like cooling water, stormwater, agricultural runoff, and return flows. So that means these are different sources that could be used. And these sources, usually you need to treat it as we call it fit for the purpose specification. That means each one of them is a site specific. So fit for purpose specification are you develop treatment requirement to bring the water from its existing source level to the water quality to the quality needed for the new application. So when you want to do it for agriculture, it's different from when you do it for industrial. So you have to develop it, and you have to put the main thing in mind is the health of the people working. So if you put water that has reused water that has some pathogens, that means the farm workers could be in jeopardy and could have human health problems. So some of the examples of the water reuse: irrigation for agriculture, irrigation for landscaping, such as parks, rights of ways, golf courses. And golf courses now, it's known to one of the biggest consumers for water, fresh water, because they try to keep it green all the time, because you have those members, they want to come and play golf regularly. So they almost water it every day, if not more, if it's a warm weather. Municipal water supply, processed water for power plants, refineries, mills, and factories. And one of the issues is to have that, because sometimes the source water, the fresh source water, could be a problem. I'll give you an example: the Monroe nuclear system or facility. Back in the late 80s, early 90s, almost shut down because the intake was full and got accumulated with zebra mussels. They blocked the water supply. So that is some of the problems you have it. So, but when you have a reused water, you're gonna apply, you have more control on that, because they were using raw water coming from the river, directly from the Detroit River or the Great Lakes. So that's why it's an issue. The indoor uses such as toilet flushing, that's a very well known. Dust control, you want to flush roads, and clean some of the areas outside. And supplying artificial lakes and some of the residential areas now in some locations, they develop some artificial lakes just for view. Of course, they advise the people, you don't swim in it, you don't use it for drinking. So they use it just for the way it looks nice. So they can supply that. Also for environmental restoration. So this table here gives you a good idea of these details like urban reuse, agriculture, impoundments, environmental reuse, industrial, groundwater recharge. Groundwater recharge, this is one of the key things they are looking at in some locations like in California and Arizona because of the water shortages. They used to depend on one of the major rivers in that area, the Colorado River, and that river now is came down to the very low level in the last few years. So the recharge of groundwater is important because groundwater usually is used heavily by the agriculture area because it's cheaper to use rather than paying for fresh water. You know. So these are a good list of what kind of things if it's like an indirect potable reuse or direct potable reuse. This diagram gives a very general way how the water cycle is. So you get your water from the lake, gets it treated, goes to commercial, residential, entertainment, agriculture, and the waste go to the wastewater treatment plant. The wastewater treatment plant treated, either it goes back into the lake or there is again a reuse application, and that is what potential to be considered, because if you see the applications, originally everybody is using the treated water like a drinking water supply, and that is very expensive. Also, people, they find like even in agriculture, you get water has a chlorine residue in it, and this is not the best. Like in many other countries, like where I came from in Iraq, back in the 60s, we used to have at home a separate raw water line for agriculture, for the house, for the garden. So that reduced the impact of chlorine and also reduce the pressure on the water treatment plant to produce, because you're going to be producing almost twice the amount in order to satisfy the demand. So in Canada, for example, there are certain applications not widely used, I have to say. Canada is only 37 million people, and we have in Canada more than 20% of the world's freshwater. The Great Lakes is 20% freshwater of the world, plus many other rivers and tributaries. So that's why there are some applications. For example, reuse for toilets and urinal flushing. Some applications for agriculture not widely used, but it is. I'm one of the people who've been pushing for that because not many people, like unfortunately, even academia, like universities, are not interested in getting into projects like that. And everybody go after. It's becoming science, becoming like politics. Whenever a new contaminant comes, everybody run after that. Like now the PFAS. I remember 20 years ago was the pharmaceuticals. So, and one of the media reporters contacted me and he said, has the pharmaceutical issue been resolved? I said, no, not far away from that. And he said, so why nobody talk about it? I said, yeah, because they have now a new one, a new item to talk about. And the problem is most of the time the politicians talk about it and people follow that because they know, and especially if you want to pay a grant, you need to have some political support to get that, unfortunately. So, so they need to have to consider a big issue here when you have the water reuse is the the health risk, especially pathogens, because if they have pathogens that could come directly or indirectly to the person, could cause a severe gastrointestinal illness. So the when you develop a comprehensive guideline, that you have to keep in mind a major issue is the impact on human health, or directly or indirectly. And that is why the guidelines need to be developed. So basically, you need, when you have these kind of guidelines, you know that you are protecting the public health. So any guideline will include values for water quality parameters, are selected to demonstrate how effective the treatment that's used. So basically, they put a table for you, what treatment you need to be used, and what is the guideline, what is the minimum, what's maximum. Pathogens, you should not have any in that, especially the parasites or bacteria, even with the total coliform, that because it will become a problem if you keep feeding it. So there is, and you need to, the people who are involved in that, they need to discuss it with engineer consultants and people who have a knowledge in that area. So, and there are some situations, for example, when they use water to flush the toilets and urinals, could make a significant contribution to reducing water use. And one example, when I went to Walkerton, we built a new, after the tragedy when 7 people died and half of the town were sick in hospital, we developed the Walkerton Clean Water Center, and we built the LEED Gold building, and we did a water reuse because as a training center, you could have more than 100 people present, and you have big washrooms. So we use the water from the labs, and and that gets disinfected again and use it to flush the urinals. So that could help, you know, to flush the toilets. That would help. That is mean you control that there is no bacteria or protozoa. If you're going to use the domestic treated sewage effluent, and that could have some of these kind of challenges. That's why you need to have certain disinfection processes that you know that is not going to compromise the removal of these compounds, because if you have by mistake, it comes in your hand, you put your hand on your mouth or on your face. If you have any E. coli in that could be a problem, or a protozoa, that could cause a problem. And sometimes the cross connection, if there is any leak, that could be a problem as well, and it could cause many people to be sick. So this is for the particular concern for the individuals, especially if you have infants or elderly people, because in infant their system is not highly developed, and also the body weight is small, so there could come a problem. And people, you know, elderly people, they might have like dialysis, could have the problems that could cause kidney damage. And in fact, in Walkerton, that strain of the E. coli caused kidney damage, and the people who died, the 7 people who died because of kidney failure. So that is what you need to have a very stringent disinfection process in order to maintain the safety of the people. The exposure of chemicals, I would consider maybe the second one, but that have always a long-term impact on people. So that's why you need to make sure that this thing does not have an issue like that. So you need to do some kind of a management for when you do the water reclamation or water reuse. So that means when you do collection and treatment from a single domestic dwelling, for example, for clusters or apartment buildings. And there is always a potential impact on people, even the small systems. Sometimes some small system could have more complex problems similar to large systems. So and potential of the The potential of some kind of contamination and all that with reclaimed water mean that there's a need to have high level of treatment reliability and oversight. And that's why when you design a water system, you don't design what's the guideline needs, because the guidelines is the minimum. You always design with a safety factor, because you could have major storm, could have a problem, and that's why you have boil water advisories happening, because the system is not as reliable or robust enough to deal with that. So you need to develop a site-specific risk assessment. You have to have people with the knowledge to come and evaluate what are the potential microbial presence in the source, and what kind of reduction or inactivation based on the current treatment. And treatment technologies, when you look at it, you have to know, compare the treatment to its capability with the existing risks. So when you have a place that is, you have a cryptosporidium, which is one of the tough parasites because it has a shield, and chlorine cannot impact any of these parasites, whatever the concentration is. And that's typically what happened in Milwaukee when 100 people died in 1993. So you need to develop systems that is capable with potential problem. You don't develop a system by the good existing situation. And that's why when I tell people when to sample, you sample when there's a heavy rain or a storm, because that's a worst case scenario, and you have your system designed to take care of that. So you need to have, what is the reliability and resilience. That is, you hear this word quite a bit these days, but the thing is, it depends on few specific or topics like redundancy, robustness, and resiliency. And I'll be talking about this now. Reliability, as I said, it's used a lot by scientists, by politicians, by regulators, because it means the ability for the reliability is often associated with the providing a consistent quality and quantity of water for the water business. So for potable reuse system, reliability would describe ability for the system to provide water that needs to provide to the public without compromising public health, and providing and reduce the use for the drinking water supply. Redundancy, robustness, resiliency describe the measures that could be taken to achieve reliability. So redundancy is the first one, and that is a typical things when somebody designs a system. You need to have a redundancy just in case. For example, you have a standby pump. So if you have one pump to deliver the chemicals, and that pump fails, that means your system is compromised, and you're not going to be able to do chemical treatment, flocculation, and all that, or even when you pump the chlorine into the system. So you need to have a backup pump. So by the time you repair that, the other pump is taking its role. And usually that has to be done automatically. Like so, when the signal fails, that is not this pump is not delivering anything. That means the other pump will kick in immediately, and that is how the design system. But in the same system, you have to be economically right. You don't put 5 backup pumps, because that's a waste. You need to look at how many pumps you need if a system fails, or one pump fail, or 2. So the other thing of the reliability is the difference from provided when you have additional treatment is needed. So, for example, if you have what we call it, and that's another topic used a lot with the multi-barrier system, and we use that for the treatment. That means if something fails, the other one will support. For example, in Walkerton situation, when we had the failure, there was a failure, of chlorine. There is more contaminants coming, plus the lack of knowledge of the people operating. Then the biggest failure was lying about it, that there is no, that's why people went to jail because of that. Even not enough, because 7 people died. And that is not, never, there is any compensation for that. So that's why you need to have multi-barrier system. The robustness is the means, the ability of system to address certain contaminants. For example, if you have, and also during a heavy storm, if you, and I'll give you an example, I served in a location, we were downstream about 2 kilometers from the sewage discharge of the city. So in a major storm, the amount of contaminants is overwhelming. So you have to have a system that could have a control to push that and to deal with that, or to kick in another things from redundancy. For example, if you have one ozone generator and it's not capable, the other one kicks in to achieve the concentrations needed based on the model for the design. So the multi-barrier system here again exhibits great resistance to prevent failures, and because you have more than one. It's like a building that stands on four pillars. If one pillar fails, the building might be still standing, but if you have 2 fail, most of the time it will go down, or 3, because no pillar will stand on 1 or 2 only. So that is general talk. I'm not going to get into the civil engineering, but that's just a rough example. So basically, when we say the robustness, that robustness is to achieve a successful ability to deal when there is beyond the actual operation happens. The resilience is the reliability of when this is the additional thing, when 1 or the 2, the redundancy robustness is not enough. The other one is, for example, combination of monitoring control to issue engineered storage buffer. So operational criteria, if it's not met, that means maybe, for example, we put in this on filters, filter to waste. If the system is not, we have that it triggers, we have what is the turbidity coming. If it's beyond that, filter go to waste. It will not go with the general flow that's going to the reservoir. No, that filter will go to waste. So the resilience, that is when you have ability to deal with that without delivering a water that have problems to the consumers. So how to validate these things? So you have to have some kind of control measures when we use the portable reuse scheme. So for example, some of the communities, like as I mentioned in Singapore, when they use it, there is a lot of operation they do between membrane and disinfection and all that. So in order to produce safe drinking water without impacting public health. And there is no different from the other sources of drinking water. And then the chemical contamination and relatively high concentration of microbiological activities could increase the focus on validating performance. So you need to look at how to achieve the performance, whatever the level of hazard reduction of problems that's happening, and if you have more contaminants and compared to the nozzle resilience and the system. So you have to develop and to have some operational criteria beyond the usual control they use regularly. So basically like a backup plan or plan B or plan C. So basically to make sure that you're able to do that. So when you have for applications to be supplied. So the evaluation of existing data and information usually are published data. Manufacturers provide data how when you operate your system, the system can deliver up to that kind of flow, for example, of chemicals. So you have to follow that, and you need the best way when you are designing to have some kind of pilot testing. Pilot testing is the closest ability to reach a good full-scale design. Bench scale is good, but pilot system is always better. So, and I'll be now talking specifically about the MENA region, the Middle East and North Africa. And historically, there's a lot of work is being done in these countries. And they did some innovative water solutions to deal with the water scarcity. Like, for example, the Gulf area, the desalination process, building dams, and in other locations like the dams, and also drip irrigation. So they've been working on that. However, we need to look at what are the challenges and how to optimize the water management for that region. So water scarcity is a big issue, and that's been identified by the United Nations, by the World Bank. And there's a study that is released by the World Bank in 2023, in January, in that. And basically, there is current management strategies across the MENA, what exists now. There's a conservative estimate of water demand by 2050. That is additional 25 billion cubic meters needed a year. That's a big volume. The reason is climate change, more high temperatures need more water, increase in population. And also, that means if you are not doing that, if you don't do management, that means you need to build another 65 desalination plants, the size of Ras Al Khair plant in the Kingdom of Saudi Arabia, according to the World Bank. So if you don't do these management and conservation, water reuse, that's the amount you need to do that, which is too expensive to build that kind of many plants. So the MENA region has been facing, in the last 10 years, in fact, a lot of issue of scarcity from lower rain levels, or also the change of patterns of precipitation that could cause problems, sometimes flooding, and sometimes there's a drought. And to sustain the livelihoods, the farmers need to have some kind of a reliable, continuous supply of good water quality. And by the year 2030, it is expected that the available water for per capita will fall below the scarcity threshold of 500 cubic meters per person per year. And that is quite low. But if you look at it that way, you go further down, you go, for example, to Africa, they are already below that level in some locations. But we are using a lot of water in our areas in the MENA groups. The most of the time, the last few decades, the MENA region focused on the conventional objectives for protecting public health and environment. Well, I'm saying that means the water scarcity, urbanization, they will have another impact because of climate change. That means you need to go further beyond the conservative way or conventional way of looking at that, because reclaimed water or reused water is a key solution for that, because that's a source. If you look at it, and I am a person who used to be in charge of water systems for cities, and when you supply water the amount for drinking water, it doesn't go beyond 10%. The rest is used for everything else, washing, irrigation, everything else. So you need to look into this issue seriously. So in the MENA countries, 10% of the area which is 10% of the area of the world, receive only 2% of the world's average annual precipitation, and that's significantly low. And contain as little as 0.3% of the global annual renewable water resources. So the average annual rainfall in the MENA region is about 250 millimeters. But many large areas of the region are very dry, especially when you go into the Gulf area, and some places when you go further down in the Sahara regions, and could be not more than 5 millimeters. So surface water resources in MENA countries are estimated to be 224 billion cubic meters per year. 77% comes from outside the region. For example, Egypt receives water comes from the Sudan and other countries like Iraq comes, and Syria comes from Turkey. So groundwater source become also limited here, which is not exceeding 50 billion cubic meters. Desalination of seawater provides mainly the main fresh water to source of drinking to the people across the GCC countries, because there aren't many, if any, of fresh waters and rivers to supply that. So, due to the limited ground water availability, the overall capacity of a new and existing desalination facility is more than 3.4 billion cubic meter on average, and that's a big number. Okay. Second here, we have something here, I think. Okay. And not just in the MENA region, but worldwide, the irrigation agriculture use is the highest for water use. And in the MENA region is almost 85% is considered for that reason, and other countries are about in 70%, something like that. So the major MENA countries, namely Egypt, Sudan, Algeria, Morocco, Syria, contributes as much as 71% of total agricultural output. Irrigation efficiency is low, however, at about 30% compared to a water average of 40%. So you compare. So it is like it is almost like 50% lower than the world average. So it's widely recognized that agriculture sector is only makes the marginal contribution to national GDPs. So the demographic growth and economics and social development for the MENA region have contributed considerably to the significant increase in water demand, producing 10.85 billion cubic meters per year of domestic wastewater. So, and urbanization, as we know, is increasing. Many people leaving the remote area, coming back to the cities. The reason is there is more services, medical, schools. Many people do that, so that means you have more demand on freshwater use. And at the same time, you have more domestic wastewater discharge. So that means you have, on the other hand, another source. You can reduce the pressure from urbanization because of that. So the average use of water from the MENA region is about 200 liters per day, compared to 525 liters in Canada and the United States. Yeah, we waste a lot of water here, and people stand in the shower for half an hour. People wash their cars sometimes almost daily basis, and also irrigation again is a big issue here as well. So and the thing is, when you supply the water to a household, you don't say you use 10% for this. You provide to them, and they use it the way they like to use it, and that's why when they use it for agriculture, for basically irrigation for the garden, that's also an amount that is significant. So, so the domestic water consumption in the Arab region has escalated to about 12,000 million cubic meter in 95, increased to 16,000 million in 2002. So you see the increase, that's a big jump. So that represents more than a 30% increase in water consumption. So reclaimed water. So again, municipal wastewater that's being treated to meet specific water quality criteria with the intent of being used for a range of purposes. And the term recycled water is synonymous with reclaimed water. So, and the problem is sometimes we have some weak baselines for water quality regulations. And again, regulations and guidelines give you the minimum. That's why always in your plan, when you operate, you have to set higher criteria for that. So because, whenever there's any problem happens, you could go below the guideline level, that is a violation, and that could impact public health as well. So climate change is now causing more of these issues. Food security is a big problem. And in the Middle East and North Africa, Algeria, Egypt, and Morocco are among the top 10 countries importing grains, although they are among the main grain producers. Net cost of food commodities imported by Arab states increased from $10 billion in 1980 to $28 billion after that. So an increase is significant here. Climate change is something many people used to deny about 10 years ago, but people realizing this is significant, and the treated water reuse could be an answer. And the issue here is not just the science. It's basically you need to we need to keep talking about the social event and social events in the media about that, because it's public acceptance to the issue that's a water reuse. And in this region, we don't talk as much about as a potable reuse, but at least for other uses. And this is the report that is by the World Bank in 2016, and it shows here the issues. You see the range of impact, and you see the variation in GDP, and you see the Middle East is the highest impact compared to the rest of the world. So we go again to a successful and efficient work depends on a good design, and you need to put the public health and environmental standard in your eye and in order when you're designing. Water reuse total is estimated is about 2.17 billion cubic meter per year. Egypt, Syria, United Arab Emirates, and Saudi Arabia are the largest users, accounting for 75% of the Arab region. And also because it's a population, and some of these countries, Saudi Arabia as well. So irrigation, that's a main thing for landscape. And it's used, I remember when I was in Qatar, I've seen this for landscape, but we've seen some challenges that some smell in the summertime. That means there is certain organics still there, has not been removed. And that's what we develop projects for that area. So how much is the share of that? So you see the treated and reused is about only 18%. Treated and unused, 25%, that discharge to the source water. Untreated is 57%. And that is dangerous, because when you have untreated sewage goes into, or untreated industrial water goes into the freshwater sources, that means potential impact on human health. So there is a need for concentrated efforts, and we need to increase this level of low volume about 20% or less, 18% we have now. We have to increase it further in order to have something significant. So the water shortages, the MENA group is about considered 14 countries in that are in the world of top 20 water scarce countries. So 14 countries of that group. So 12 countries of the Arab and Western Asia region have less than 500 cubic meter a year for renewable water resources. And here it shows this is the January 23rd this year, January 2023. It shows the highest impact stress in the countries, and you see this is the MENA group is the highest, and you see it here. And there are some sectors here, but this is a big group here. And so for renewable water sources per person, and you see here certain countries, and you see here the lowest here when you find some countries going to find them because the water sources, they don't have as much rain in these countries compared to Iran, Syria, Morocco. They have more rain compared to these countries. And here the non-conventional water, and you see Qatar, and Qatar has small population as well, but the impact they're doing, it's useful for some of these approaches. And these are the high income countries, and you see a better situation here than middle income countries, and here low income fragile economies here. Excuse me. And that is the report, most updated report from the World Bank about the expectations. And they have economists and people collect data from on-site to come up with these details. So there is also providing water to this area, and you see how much coming from North America, from other countries, Eastern Europe and others, even as far as Australia. And that is because, there is not enough, and many of the people here, you find it, drinking water from the bottles. And many people don't have any faith in the water source supplied to the tap. And the sustainability here again shows the issue, how much desalination and how much reuse, and what is the groundwater sustainability. And Morocco here is in better shape than countries like Libya because of the weather conditions, the water resources, all these countries and that's again, a recent study was done at that time. Food and Agriculture Organization, United Nations developed that study as well about the irrigation water productivity. Israel, Jordan are close to each other's, and you have again Libya is one of the lowest here in the area, followed by Syria and Iraq. And that is because of the political issues, the wars, the fighting. So you lose a lot of the value of the system. Some of the systems are not working anymore because of that. So we talked quite a bit here about this. So mainly the water use agriculture is the highest, and it is predicted that agricultural productivity in the region to drop by 25% by the year 2080 due to climate change and water scarcity. And that is an alarming. That means you will have more dependence on other countries to supply you the water, bottled water and others. And Qatar, for example, has been reported that production of treated drinking effluent increased from 24 million cubic meter in 2004 to 117 million cubic meter in 2012. And it's known because of the construction, the population, work population, all that. And that could change because of the, especially the World Cup is finished and most of the buildings and construction is done. So there will be some reduction in the use. But at the same time, there could be more projects happening, and it is expected that about 67% of the TSC for agriculture, but basically was irrigation mainly. So now we're going to be talking more on the science on the issue. So the effluents has many challenges like pathogens, biological or organic demand, BOD, COD, phenols, cyanides, and a complex of chemicals, pharmaceuticals, endocrine disrupting compounds, personal care material. So they need to look at advanced treatment technologies because the regular treatment, wastewater treatment, activated solids and all that, that's not going to be the answer, because you're going to dump that sludge somewhere in the landfill with rain that's going to bring these contaminants back to you. So you need a technology that degrades these contaminants. Ozone is a proven technology for oxidizing and reacting with many complex chemicals. Ozone is, if some people don't know, could be produced in the air. When you have any lightning, an electron breaks the molecule of oxygen, which has two atoms, into those atoms. So this, will be broken into two. So one of these atoms will attach itself to the oxygen molecule and become ozone, the three molecule atoms of oxygen. But it is a reversible reaction. That means ozone is not stable, and that's what makes it very reactive. If the gas is stable or chemical is stable, it's not as reactive. But if it's unstable, that means it's very reactive. And this is what we just said, how it works when you have electric discharge here, like what happened with the electron. You break it into two atoms, one attach itself, so it becomes O3. Advantage of using ozone: disinfection for parasites, bacteria, and viruses. The algal toxins, oxidation, taste and odor control, improve water treatment processes, reducing trihalomethanes, which is a carcinogen from chlorine application, removal of PPCBs, and the cyanotoxin degradation. So when we look at how strong ozone as an oxidizer, you see this diagram gives a good example for that. So you have ozone. What is the CT is the concentration and time required to achieve the oxidation or disinfection requirement for pathogen. And the study was done on 3-log GRDA assist inactivation. So what's a 3-log? That means 99.9% inactivation of GRDA And Giardia is also a very dangerous parasite. It's fatal, could be fatal, and should be zero in the water, drinking water. So the study was done by the Water Research Foundation in the United States at 10 degrees C and pH 7. They found you need 1.43 CT for ozone. Chlorine is 112. Chloramine, which is chlorine, and ammonium, 1,850. What does that mean? For example, if you have 1 milligram per liter of ozone, that means you can inactivate this Giardia in 1.43 minutes. But if you have 1 milligram per liter of chlorine, you need 112 minutes. And if you have the chloramine, 1,850 minutes. That does that mean typically this is like a contactor size. So do you want to build this size or that size or that size? That's about 80 times bigger than that. So it is economy. So you can produce that, and also fast, because when you build that, most of the water treatment plant or sewage treatment plant are within the cities. So you don't have the space to build these kind of contactors. So using a chemical like ozone, a gas like ozone, can do the disinfection processes and other degradation of other chemicals in a very short time. And this show you the amount of increase in sewage treatment plants in the United States up to the year 2020, a significant increase from the early 80s. The country that is a leader in the ozone use is France. The first ozone plant used for drinking water was built in 1906. That's more than 100 years ago. So, and well, of course, they upgraded the equipment and all that. There is still a plant with ozone in Nice, France. And if you go now to Europe, most of Europe is using ozone. France, Britain, Germany, and many others are using Switzerland. Switzerland is the most strict in the issue of contaminants use, and they are using a lot of ozone and ozone-based advanced oxidation. Japan is also one of the leaders in the applications of ozone for water and wastewater treatment. So ozone is a powerful oxidant and reacts with the PPCPs is the pharmaceuticals and personal care products, and EDC is the endocrine disruptors in water system. These compounds could cause cancers. And also we've seen, I presented it in previous presentations, is it has an impact on some of the species in the water, like fish. Some of the studies shows that it impacts the fish, and the male fish start to produce female organs as well. And the shape of the head of the male fish looks like the female fish. And they call that the feminization of fish. So that's a very well-known topic in the industry for the last more than 10 years. It's been the work on that has been going. So you need to look at what kind of parameters you want to reduce, what kind of organics in the water. We worked on a study in the city of Windsor, and we did an evaluation on how much of some antibiotics, because of the World Health Organization did a report collecting data from 114 countries, and they found that the biggest issue they said in the next few decades is the antibiotic resistant era. And we've seen outbreaks in hospitals and in locations. Somebody goes there, he has some, for example, breathing problems, and leave with skin rash for MRSA or others. So these kind of things, because antibiotics is not as effective anymore because traces of these antibiotics are going out in the wastewater effluent treated because the regular treatment procedures are not effective. So the study, we looked at 3 antibiotics. One is chlorotetracycline, which is a very well known in the application. And the other one is enfloxacin, and the other one is gemfibrozil. And those are why we picked them because we found them in the wastewater discharge quite a bit. So that means the use by the public or other applications, hospitals and others need us to look into that. And in the study, they look into certain reference compounds. And we don't have to worry about that because this is a pure chemistry for the HPLC work in order to get these reagents and all that. So basically, when we looked at these compounds, that we found, like, some of these reagents could provide higher grade quality. These are the 3 molecular structures, chemistry structures for those compounds. The gemfibrozil is at the top. Molecular weight is 250. Chlorotetracycline is 515. And that's, you see, that's a high molecular weight. And for enfloxacin, it's 359. So it is an issue when you have that kind of compounds. And these are, you see at the bottom, the studies and the sources to obtain this data. So in this study, we found out that when we apply small amount even of ozone, not a high amount, we were able to reduce these compounds, significantly, in a very short time of the reaction. And you see here, and each chemical is different in it because of the chemical structure, each chemical is different. For example, this one, the tetracycline 1 CTC, is the highest in the reaction. The others, the ENR are less. The gemfibrozil is the slowest. So you see, that's why when you're going to do a plant and you want to see oxidation for that, you have to keep in mind you deal with the worst case scenario, which is the gemfibrozil here, in order to get the reaction. And this is because of the chemical structure of this compound. So the degradation of the pharmaceutical substances was higher at the CTC than the NR, and the GM, gemfibrozil, was the lowest. So overall degradation was increased from 81 to 100% when we increased the ozone dose. So ozone dose was key. So it increased here from the CTC from 81% to 100% when we increased it from to 35 micron. And the other one from 53 to 82 and 34 to 76. So a major reduction in that. So the ozone oxidation, other studies done by Shane Snyder, who's now at the Nang Institute of Technology in Singapore. He used to be at that time in Nevada, working with the municipality. He did the studies and he looked at ozone and the ozone-based advanced oxidation, which is ozone plus hydrogen peroxide. And the thing is, and this is the ozone is a little bit selective in the reaction. But when you put more hydrogen peroxide, the hydroxyl radicals make oxidation more unselective. So it means it goes with all of it here. So bench and scale, as I said, is important. So you could know what kind of concentration you need to use in order to provide ozonation at that level. And here the tables shows the amount of ozone and hydrogen peroxide, and you see the different compounds, and you see ozone a percentage removal, and based on also reaction time. So reaction time is not very long. You have reaction, then you see it becomes steady here. So a very good study was done at that time. So what we did a project in Qatar during the time I was working there, in 2015-16. So we wanted to investigate how useful would be the water used for treated sewage effluent. As we said, the population is increasing, the demand is increasing, and more treated sewage effluents coming out. And they have like lagoons there, and they use it afterwards to for irrigation. So the discharge from sewage treatment plants, as we said, it's increased, and there is a lot of evaporation from that. So that means what's left will be higher in concentration, and that is when become a problem, you know, when we do the retreatment. And the sewage treatment plant is a giant collector of human pathogens and other activities. So what are the challenges for treated sewage effluent? Seasonal changes, presence of certain organics and chemicals that might have an impact on operation and equipment, pathogens, chemicals of emerging concern, pharmaceuticals, we said those, and chemical and different disruptive compounds. The PFAS, which is that's what we hear about now, what's coming from the non-stick surfaces, or even for the use in by fire retarding the clothing and others. And so these are some things, and also odor and color. So why we have to be concerned? The reason is, especially for the pharmaceuticals and others, chemicals of emerging concern, these compounds were developed not to biodegrade quickly, especially for pharmaceuticals, because the idea, they need to stay in the body in order to reflect, to have an effect on, for example, if you have sickness or something like that. So human health could be not, sometimes people don't understand how significant this issue. And when people say, I remember one time one person argued that the concentration nanograms per liter is nothing. I said, yeah, but you're looking at using it every day. You have that kind of complex addition of these compounds. You have hormones, you have all kinds of medications for high blood pressure, cholesterol, others. So together, it is a problem. So rainfall in Qatar is basically between the months of December and April, and the period that time, 1962 to 92, was very low. In 2012, the whole year was 23.9 millimeters only, according to the study provided to us. And that would show you the rain at these locations. And you see it's not much, and different times of the year. The annual precipitation versus like the here, and so, and you see here the that is the annual precipitation, and you see here the amount of use here, how much. As we indicated earlier, the water consumption has been increasing, and when we have more population, there is, according to the figures we had at that time, close to 1.5 million workers, including us, who came to the country to work. So, and there is water, as we said, the major amount is being used for agriculture, which is estimated as 271 million cubic meters. And private household were the highest, 295, because here you have also swimming pools, and that's big amount of water and a lot of evaporation. And government use, that's whatever things, applications they use for their buildings, for their, laboratories and others. So these figures show like agriculture is always the biggest issue to focus on in order to reduce the demand on the freshwater supply. Here again, it gives you how much is for the treated sewage effluent, seawater desalination, public supply, and groundwater abstraction. And you see certain time agriculture is the highest application on that. So we developed a design for a pilot plant using different technologies, because one technology, there is no one technology can deal with all these issues. And we submitted a patent on that plant that was built with a SCADA that is able, that means collection of data, automated. You can run the system 24 hours and you can collect the data, and some of the analysis need to be done in-house. The main focus was on the removal of pharmaceuticals and other compounds that comes in the municipal water. So the regular water treatment systems, the wastewater plants, it's known that is not able to remove these compounds, and that's why the significance of this kind of application, how much you're reducing the contaminants coming out and getting consumed by the public. A study we did, as I indicated, the Great Lakes, and that's what we try to make people think about it seriously here between Canada and the United States. 1,448 sewage treatment plants discharged into the Great Lakes. And you have populations, for example, you have Chicago, I think 8 million something. Detroit used to be close to 2 million. You have Milwaukee and Wisconsin, the state of Wisconsin. So there are 80 states around the Great Lakes. And so that means there is a big issue of these compounds are going, and most of these treatment plants have no ability to remove these compounds. So treatment technology could play a big role. So the ozone oxidation plays a big role. The oxidation ability of ozone, as we compare to chlorine and others, is way higher, in addition to its ability to inactivate the pathogens like Giardia or Cryptosporidium or the viruses. So these things, it's able to remove these compounds. The pathogens, as we said, indicated, but when you have a system like ozone, the removal of these contaminants, the pathogen is not a problem. The biggest issue is the other chemicals that we are dealing with. So, this system includes the pilot plant. We use membrane, we use ceramic or polymer UF. We ended up using just the polymer UF because the ceramic was not available at that time. And the oxidation process, you could use ozone by itself at multiple stages, or ozone and advanced oxidation, ozone and hydrogen peroxide. This is the schematic for the system. So we developed, just in case you can't get the sewage water, because you have to have certain permits to bring it into a building. So you can develop your own sewage discharge if you don't want to include a human waste or something like that, and it's easier. So you just add chemicals to mimic, or organics to mimic the waste. Also, pH, you can control it using the CO2, carbon dioxide, and you could measure it that way. So, and you could, and we use application. We looked at the use of certain application like flocculation and sedimentation. This was much more, how can I say, lower in cost for operation compared to reverse osmosis. That's what many people are going to say. But the thing is, when you do reverse osmosis, you have to add some of the other chemicals that you need. It depends what you're going to use this treated sewage effluent. And you don't want to use water that has no anything left in it as well. So what we did here, we thought we used that, and this is significant use. It could be more space, but also reverse osmosis systems are not small in size to include for a big volume like this. However, this would need more manpower, to operate, and also to monitor by manpower, because everything was done automatically. Chemicals are added based on the concentrations required. Sedimentation, usually place settlers, and the solid discharge goes out. Then water goes into this filter. We could become a biologically active filter. You could use sand. That could take longer to produce the biological activity, but if you use granular activated carbon, the development of biological activity is faster. And here you have the two membrane system we use, for that. And this is the system. You see a view of these tanks, and everything was designed from stainless steel. That's another section from the system. And this is, we developed the ozone contactor in plexiglass. We tried to get the glass, but the manufacturer said any pressure could break it. So anyway, so we use this plexiglass, a certain method that does not get impacted by ozone application. So that was built and start to be used. And my understanding, they are doing some tests on it right now in the one of the sewage treatment plants. And so this would impact if you have a good quality of treated solids, you have less demand going to be on the desalinated water, because you could be watering your gardens, washing your driveway, of these compounds, because everything is supposed to be clean and does not cause any potential health issues. So that is what the project would provide, a knowledge to how to operate a system, how to reduce the application of the use of water, fresh water, and maintain a good health system. And here it shows what you achieve in a way. Here you have raw water, you have developed drinking water, then some become wastewater. So you do secondary treatment, the tertiary treatment, and then the advanced treatment, with part of it is water reuse and all that. And then at the end it is water reuse at the end. So you need to develop certain planning for the municipal water systems. And that based on your system, how you can do it, what is the source of the water, what is the volume required, what is the demand. So, a system was developed by that. The US EPA developed a certain process and program, basically a plan, how you would deal with the challenges that facing your water system. So you would be focusing on border water resources management options that would consider all water resources within the community, and also the holistic planning method. So there is a diagram will show how you use it with the planning and when without. So if you do traditional water management, traditional, that is non-integrated water resources, you have, this is the receiving water, you have like a river, goes to water supply, and you know, like the wastewater discharge, the effluent here, plus the water supply, could be well, could be fresh water, and then goes to the, after you use it, the wastewater goes to wastewater system, and if it's here of the storm water as well, provide the from when you have rain outside, and there's another issue, could be from the combined sewer overflow as well. So but with the management system, so you look at some beneficial reuse of the storm water, and that will is coming like from the storm sewer. Some of it dry event, you're not impacting it, but the storm water, there are studies being done in the last 30 years on beneficial reuses. And also, if there's any wastewater reclaimed water, you add it to the water supply. So you see, with that approach, you're looking at how you reduce your demand and how will you reuse the water supply in a more efficient, innovative way. So basically, you're determining the control, some control of the impacts, like environmental impact, climate change, all that. And the integrated management system will improve the opportunity or the opportunities to obtain benefits from water, regardless of the stage of the water cycle is. So the concept for the integrating water conservation practice to reduce the demand for fresh water are part of the comprehensive management approach. And you see here typically used in households, you have rain and it comes down, and there's disinfection, rainwater storage tank, and there's a meter, and there's here typically putting disinfection and to deal with the water, and could be some used, reused, to wash for the washing machine. So end result of integrated water management is to reduce discharge to receiving waters and reduce reliance on surface and groundwater supplies. And like I was in my teaching to course, most of the students were international. In fact, almost 99% were international, mainly the group from India. And the water scarcity and water contamination is a big issue there. Even when you think it is a nuclear country and all that, but still there are issues in the drinking water supply and the drinking water reuse. So these are some of the management strategies you need to look at. Water conservation, reuse of wastewater, reuse of gray water, stormwater, BMPs, best management practices, rainwater harvesting, enhancing groundwater recharge, increase surface water detention, add weather urban runoff treatment, dual plumbing for potable and non-potable uses, separate distribution system for fire protection, multiple purpose infrastructure, and use of the right water quality for intended use, and green roofs. And green roofs are basically, they put it on certain buildings, basically reduce the heat that's coming from the sun, and also give some view and reduce water waste that goes down drains. The other one is the low impact of the development. You need to look into that as well. So this approach of the integrated was applied, in fact, in Los Angeles, in California, and that's been a very successful approach. and the IRP, the Integrated Resource Plan. And that approach has been known and been used by other cities in order to find out how can they optimize their application. So basically, the goal was to develop multi-purpose benefit strategies to address the chronic droughts, achieve volumetric compliance with water quality. So all these things need to be studies when you do that. And the study, and Professor Majid Mohseni was partner with me. He was one of the people who worked on study for a long time. Also, he developed and that received in 2006. The IRP received the numerous awards for that approach. So project planning things, you need to further examine the project viability, identify quantity of reclaimed water available, screen all existing and potential future users, identify potential users, determine if users will accept reclaimed water, because that things, before you invest millions to build a system, you need to have a survey to find out, do the people agree with that or not? Compare supply to potential demand, prepare distribution system layout. When I say they accept it or not, they don't accept it because they don't understand it. So that's why the role of the municipality and the government officials is to explain to the public and show them the advantages. And also you need to finalize customer list, determine economic feasibility, compile final user list and distribution, prepare point of scale facilities, obtain regularity approval, perform on-site retrofits, perform cross connections test, and begin delivering water. Here is another diagram to show you the activities here. That's the water reclamation plant. Here is the water plant. And places like Brazil, in fact, they've been active in doing water treatment for their car wash. So basically, they were able to develop about storage capacity 2640 gallons, which is 10 cubic meters. And also they developed a certain guideline for that. Is hand-operated car wash, oil water separators, wastewater reservoirs, and FCF calculation column. And you see here, and this has been used for the car wash. And so you see the, sometimes you might alter or change one. Like a week ago, there was something is down. So they looked at the situation and why this thing happened. In many cases, the water reclaimed distribution system should provide reclaimed water to diverse customer base. The urban use customer typically include golf courses, which is, as I indicated, heavy users. And in some cities, example in the US, they provide water for cooling, wash down, toilet flushing, and irrigation.
Doctor, we need some time for discussion, please.
Okay. Yeah, almost done. Yeah, basically, that's the last slide.
Okay, yeah. Thank you.
If there is any question, yeah.
Okay, maybe, first of all, thank you very much for this huge information. And it's very important to this overview is important because it shows how difficult to make things clear before starting a project. It's very important. And since you have sent us your presentation as PDF, everyone can see it again, and he can also go back to you. But let's see the chat here. There are just one first question at 2010. It's about the membrane. The guy, I think, is Mohammed Humad. He thank you very much, and he say that he want to know about the application of nanotube to enhance water purification. That's the question.
So the question here about the permeability, these membranes, about the desalination. This thing we're talking about is this is the water treated sewage, the wastewater from applications, not the desalinated water. With the pilot plant we designed, we included membrane in that as well. But the thing is, this is our focus, not the salt issue here. Is basically the contaminants, could be pharmaceuticals, could be other things, and also the sewage. It's a human waste. That is what we try to, and most of the treatment processes, unfortunately, like we've seen, the amount of organics and that over 5 milligram, more than 5 milligram per liter, which is high. And that's why you see a smell in warm temperatures if you put it for irrigation. And also when you have organics is a good way to hide the pathogens and other chemicals. So when you have those on the grass and rain comes afterward, or you water it again, you're spreading that as well. And there are certain bacteria and viruses, they could stay alive for days. I'll give you an example. The COVID-19 could stay on surfaces for 3 days active. And there are certain viruses could stay up to 9 days active. So that's why you need to have a strong disinfection system. That's why when we talk about the ozone is, as we show the diagram, is about 80 times more active than chlorine. And with the use, and the most of the wastewater treatment plants, they use UV. The UV, I don't think it is that effective, and we've seen it because when we did our studies, we're getting the discharge from the sewage treatment plant with full of organisms, microorganisms. The reason is UV, you need to have a very clean water to have the light to go through. And usually that sewage discharge is not that clean. Usually it's colored. You see it most of the time, it's colored. When you have 5 milligram per liter, you see that is there. So basically, that's what you need to have to look at that. And we did it in our studies. We've seen these pharmaceuticals, you're able to remove it with the oxidation with the ozone.
Okay. So the Professor Ihlal, he just want to know about the relation to the your talk to the nexus, water energy nexus. How can solar energy promote the reuse of treated water, wastewater? You can see his questions here. I can again, how I think he's here, Dr. Ihlal, Professor Ihlal, if you want to reform your questions. Hello. So
solar energy can be used definitely for supply, and especially you know, in the MENA group, which there is plenty of sun, and you can produce the energy required. Basically, if we don't use the energy from the you know, the conventional energy system, take it from there, could be used from solar system.
Okay.
And in fact, many systems now in China and they've been start to use the solar energy more effectively compared to 20 or 30 years ago, because the increase, well, they have a huge amount of population, big industry operation, so they need to reduce, and they have to buy fuel from outside the country. They have to buy oil. They can't afford keep buying increase in the amount, and the fuel cost is increasing. So solar energy is basically, I'm not saying free because you have to do maintenance and all that, but it is the way for future, no question.
Ustad Salim, can you open the microphone of Ahmed Ihlal?
It is opened and he is there
Yeah.
also.
Yeah. Thank you. But I was thinking, thank you so much for your nice talk, and thank you for the organizer of this talk. I mean, how solar energy can be direct use to treat water, not to fuel.
Well, you see, the sun in general considered as a disinfectant, but a very weak one. For parasites, you're not going to be able to do anything. Viruses, you're not going to be able to do much. Chemicals, so you need to have, with the oxidation requirements for pharmaceuticals, endocrine disruptors, you need to have some strong oxidants. Sunlight might remove something, but is not efficient to do that.
Yeah, thank you. I have a second question, if you don't mind.
Sure.
You are talking about storm water. What do you mean by storm water? Is this
Well, yeah, like from rain and all that, you know,
Okay.
like we have it here, for example, in Canada.
Okay.
There are like open pipes coming through the city, and that water comes through, and that is, and see, the problem is that that's what they have it, something, the combined sewer overflow. And that could impact the sewer when there is heavy rain. And so that's what it is need to be discussed typically with the designers and all that. But yeah, this is where you have that, and especially this is one of the countries where have a lot of rain. Yeah.
Thank you so much.
You're welcome.
So is there any questions from the public? Please go ahead. Just show up that we can open your microphone. If not, then I have one question, Dr.
Sure.
Saad, regarding, you know, everyone now is talking about smart city. And by listening to you, I find that the process, your process with all sensors and all this stuff can fit or can be integrated to smart city.
Definitely.
I think it will be very interesting that in every region, that if there is a problem of water, it can be resolved by this method of ozone in this kind of new style of living.
And you can produce ozone from air, so you don't have to bring, and with these low concentrations you use, you can produce it from air.
Yes.
I built a water treatment plant in British Columbia, 15 milliliters a day. And we used ozone for oxidizing arsenic and manganese.
Yeah.
And we used air. And that is, we finished it in 2019, before the pandemic. When the pandemic happened, there is a more demand on chlorine. So basically, we put only chlorine when it goes into the distribution system, so to maintain water quality in the pipes. So basically, everybody was fighting for chlorine, but we didn't need as much because the main oxidation process we're doing it is from air. And that is also the thing, it is, you reduce your footprint for plants this way.
Yeah.
Well, reducing footprint is basically you reduce energy use, you reduce trees or plants you have to cut to build a new building. So reducing footprint is an important now for the reducing energy use.
Yes. Yeah, yeah. So thank you very much, Dr. Saad. I'm
My
sure
pleasure.
we will let your address and your detail that if any one he want to contact you, if industry in Morocco, for example, are interested in your method,
Yeah.
you can also
And that's why
contact.
my last slide, my email is there. So anybody is interested,
Yeah.
I'll be more than happy to answer
Yeah.
questions. And if I
Okay.
don't have the answers, I know who to talk to get the answer.
Very good, very good. So if anyone, you have the last chance if you want to ask now. Otherwise, you can always send us your questions and we can forward it to Dr. Saad. So, okay, thank you very much, Dr. Saad. We are
My
really
pleasure
very
always.
happy to have you in this university, and
Thank
we thank also Ustad Salem for giving us this opportunity through the Zoom, and he is also with us behind the scene all the time. So thank you for all attendee, and see you next week. I will send you the information about the next talk. Thank you very
Thank you.
much.
Thank
Thank
you.
you. Thank you.